All right, Chapter 5 is stuff that you've usually seen in other classes besides this. I will on Blackboard provide some examples in the text that you should look through. I wanted to mostly just provide a brief overview of some of the big ideas in Chapter 5, particularly the ones I thought were most important. The first thing is that in math we have an order that we say things should happen in. And this order has the mnemonic word PEMDAS. This stands for parentheses. In your book, they call this grouping symbols. This is more accurate because it's not always just parentheses. You can have parentheses, you can have braces, you can have brackets, anything you like. You can even have the fraction bar, the numerator and denominator of a fraction bar. The fraction bar is also something that separates things into a top and bottom, left and right sort of deal. So you do all the stuff inside those parts first. Then you do exponents. And under exponents, again, I'm going to maybe write in here, insert some exponent laws that we might have. Remember, if you have an exponent process here, this x is standing in for any of the numbers, and we usually think of n as some sort of number, natural number, 1, 2, 3, 4, 5, 6, 7, something along that fashion. So if I have two things that are the same base, and we'd call x the base, if I've got two things of the same base, and one of them's to the n and the other's to the m, our rule in the textbook says we just add the exponents. An example of why that's true might be if I have x squared and x cubed. What does this mean? Well, it means I have two x's and then I have three more. Altogether, that's 5 x's, which is what you get when you do the addition. Contrast this with if I have x to the n and then parentheses m. Here the book rule would say to multiply these two together. If I think of x squared cubed, what am I really saying? Well, the cube part says I've got 3 copies. Maybe I can't spell copies, but I've got 3 copies of x squared. So I have x squared once, twice, 3 times, 1, 2, 3, 4, 5, 6, and that gives me x to the 6, and 3 times 2 is so much 6. So you can always work out some specific examples of the stuff you want. We also have the general fact that no matter what we're talking about, anything raised to the 0 power is always going to be 1. You've already seen this in the exponent section for binary numbers. We talked about that first binary column being the binary ones column. Of course, this requires x doesn't get to be 0, because that would be messing with our heads. 0 to the 0 maybe isn't a good idea. And then we also have maybe this new one. If I have x to the minus m, I can rewrite this as this. Let me do an extra step in here. X to the minus m is the same thing as x to the minus m divided by 1. There's a secret coefficient to x. It's the number 1 up here. There's always that hidden 1 in front of numbers. We never write it, but it's there. And for negative exponents, well, I'm going to keep that 1 that's up there on the top, and I'm going to pull the x down below. So now it's an x to the positive m. When you switch sides, it changes the sign from a negative to this positive m that I've got right here. And then since I never write this coefficient, a positive 1, we just write this as a 1. Maybe I'll write 1 a little bit more naturally to what we've been doing, 1 over x to the m. So if you have a negative, you're allowed to pop it to the other side of the fraction bar. So I've got grouping things, which is parentheses. That's the P part of PEMDAS. Then I've got exponents, which is E. Then I have multiplication and division. Multiplication and division. These you do from left to right in the order that they appear. And then lastly, I've got the A and the S, which stand for addition and subtraction. So these things all together give me the expression PEMDAS, and it's how we understand what order to work some math equations in. And this is important because if I have something like 3 times 4 plus 2, which I almost think I've done in a video here earlier on. But if I have this, well, without the PEMDAS rule, I could theoretically get myself two different answers, because I could either do the 3 times the 4 first and get myself 12 plus 2, which would give me 14, or I could do the 4 plus 2 first and get myself 3 times 8. 3 times 6, maybe I can't count today either. I can't spell and can't count. And 6 times 3, as we know, is going to give me 18. From PEMDAS, I know that the multiplication is the more powerful one. So I know that the correct way to do this is to do the 3 times 4 first and then add the 2, making this the correct final answer of 14. And that means that this part right here is not correct. In addition to talking about this order of operations and understanding things like this, we've got a couple other things we do in this section, in the exponent business and whatnot. One of the things that we talk about in this section is fractions. So here's some of the fraction laws. If I'm adding two fractions together, I can only add them like this. I add tops to tops, but to do that, the two denominators, we call the bottom part of a fraction a denominator, and we call the top part of fractions numerators. The denominators on the bottom have to be the same. If they're not the same, I have to make them be the same. For example, we know that if you're adding 1/3 plus 1/2, let's do it differently. Let's add 1/4 plus 1/2. Well, I can rewrite 1/4 as 1 over 2 times 2. And this gives me 1 over 2 over here on the other side. To have the same denominator, I want them both to have 2 times 2. This guy only has 1 2. This is the idea of a lowest common denominator, least common multiple that you've seen in some class long, long ago, probably in grade school. To make this happen, I need to get another times 2 down here on the bottom of this right equation so that they both look the same. But I can't just go multiplying by 2's on one random side of the fraction bar, so I have to multiply by 2 on both sides. This lets me keep this equation balanced. That's because you and I both know that 1/4 is the same thing as 1 over 2 times 2, and that 2 over 2 times 2 is what we call 2/4, and we all know that 2/4 of a pizza is the same as 1/2 of a pizza. From here I would add tops to tops and get 1 plus 2, and I would just keep the same bottom. Notice, the bottoms have to be the same, the denominators have to be the same, but you don't add them, you just keep them. This gives me 3/4. And that's the answer we want. If you tried to do any other process than the one I've just done, you wouldn't be talking about the right shape, because let's look and think about a pizza. Well, what have I got? On the one hand, I've got 1/4 of the pizza, and on the other hand, I've got 1/2 of the pizza. We know this has to add up to 3/4, and so this is what lets me power my idea that I better have the same denominators, and that I'm just going to add the top parts of the denominators together. I can't do something crazy like add the 4 and 4s and get 8s, because 3/8 is so much not 3/4. So you've got that. It works the same way for subtraction. If you've got two fractions, you have to have them have the same denominator for subtraction before you can split them up. This rule works both ways, incidentally. If you're talking about some things, let's look at this. Maybe you're already aware of the fact that since we wrote 2/4 as 2 over 2 times 2, you can do this cancellation thing and reduce this down to 1/2. So let's look at how this plays out with some addition. What if I have 2 plus 4 over 8? Well, I can rewrite this as 2 plus 4 over 2 times 2 times 2. And I might be tempted to do some cancellation, which would be a perfectly fine thing to do. Before I do that cancellation, let's look at what I'm really dealing with here. On the one hand, for sure, I know that 4 plus 2 is on the top part of the fraction bar. That's one of my grouping things. That's part of the parentheses business. So I know that I can add those together right away. This gives me 6 over 8, and we know what 6 is. 6 is 2 times 3, and 8 is 2 times 4. I can do the cancellation and call this 3/4. However, when I'm looking at this, there might be some cancellation I want to do. Let's take this down here and do that 2 plus 4 over 2 times 2 times 2. Question for you. Can I cancel these? Yes or no? Well, let's look. If I do cancel those, what have I got left? Well, I canceled the 2's out, so I'm left with a 1 plus 4 over 4. Because I canceled this 2 down here, and 2 times 2 gives me 4. This is the same thing as 5 over 4. Either way I work this out, I better be getting the same answer. We already know the answer is 3/4. 5/4 is really not 3/4, because 5/4 is way bigger than that. So the answer is no, I can't do the cancellation like this. This process that I've just tried to do is wrong. It broke something. What it broke was this. I was going and canceling the 2 2's in front, but I was completely ignoring this 4 over here. And that 4, it deserves something. So let's look at what I should have done instead. I've got 2 plus 4 on top, and I've got my 8 on the bottom. We can engage in a process called factoring. If I pull a 2 out of this 2 here, I've only got one thing left. If I pull a 2 out of the 4, I've got a 2 left. All of this is over 8. Again, I can rewrite 1 plus 2 is 3, and I can rewrite 8 as 2 times 4. Now that the top part of the fraction is only multiplication and the bottom part of the fraction is only multiplication, I don't have any more addition, now I can do the cancellation and get the 3/4 I was expecting. Let's zoom in on this process here because it's going to help us understand the next chapter a little better. We have this idea and this rule in math called distribution. It's usually written like this. If I have A plus B, A times B plus C, you know that you do the stuff inside the fraction first, but B and C are letters. I don't really know how to add them together. So there's this idea called distribution that lets me say, well, I multiply the A times the B, and then I multiply the A times the C. And that's really what I was doing when I took this 2 and this 1 plus 2 and grabbed it out of this 2 times 4. Because what I was really doing was this. I saw 2 plus 4. I realized that 2 plus 4 was really 2 times 1 plus 2 times 2. I looked at this first thing here, which was both 2's. I let that stand in for A. And then instead of going this way through the equal sign, I went to the left, pulled that 2 out in front. And what happens? Well, you pull the 2 out in front, and then you're left with the 2 different parts inside. So I pull the 2 out in front, and what am I left with? I'm left with a 1, and I'm left with a 2. You know that 2 plus 4 is 6. We also know that 2 times 3, which is what 1 plus 2 is 6. So this process, at least I have an example here that convinces me it works. So this is called distribution. When I have parentheses, and I do A times B plus A times C, and distribute this guy through to both these terms. I don't just have to have a B and a C. I could have B plus C plus D. And I would do AB plus AC plus AD. You distribute the A as many times as you need to. Which leads me to almost this business up here of going backwards, like we did to make this pull out. When I went here and grabbed the 2's out here as separate pieces and pulled them out in front. This is sometimes called factoring. You're going to see it a little more in the next section, but it helps us in other places as well. So let's talk about square roots. In a class other than this one, you're probably already familiar with the fact that the square root of 4 is 2. The formal rule is that whatever you're looking at inside the square root of something is going to be the stuff that I use to make it multiply together by itself twice to get that thing inside. It sounds kind of wordy, but what I'm really saying is that 2 times 2 equals 4. Since I can take 2 copies of this 2, multiply them together and get 4, and that's what tells me the square root is this. Same idea with 9. I'm asking what times what equals 9. And the answer is, of course, 3 times 3. So the answer to square root of 9 is 3. So now let's take some square root facts. These facts are these ones. If I have the square root of one number times the square root of another number, this is the same thing as if I have the square root of the 2 numbers times each other once inside the radical. We call this part the radical. Same thing for division. If I have root A over root B, I can just take one square root and think about A over B. This is true for multiplication and for division. It is not true for addition and subtraction. Let's look at an example of these things. If I've got the square root of 4 times the square root of 4. We know this is really just 2 times 2, which is 4. If I use my rule, that tells me it's the same thing as the square root of 4 times 4. That tells me it's the same thing as the square root of 16. I know that's 4. They match up here in this way. On the other hand, if I talk about square root of 4 plus square root of 4, this is called 2 plus 2, and this gives me out the answer 4. On the other hand, if I try to convert this, maybe I'll do this in red, and I'll take the process here, but anytime I write stuff in red, you should be suspicious of it, because I might be trying to do something that's wrong, that's illegal mathematically. If I try to make this turn into 4 plus 4, and then do the radical, well, what am I saying? I'm saying this is the square root of 8. And what do we know about the square root of 8? Well, 8 is 2 times 4. And by my laws, I know that's this. And that equals the same thing as this, which means 2 times root 2. And 2 times root 2 is not the same thing as 4. So that means all of this was very, very much wrong. You don't want to do that. It's not legitimate. There's not a rule in my book that says I can, so I really shouldn't have thought I could. So that was so much for multiplication. It works for division as well. If I've got something nice, like the square root of 16 over the square root of 4, I know this is just 4 over 2, which I know should give me the final answer of 2. But if I convert it to one huge fraction inside, and then do the radical, well, 16 divided by 4 we already know is 4, and the square root of 4 is 2. So these guys matched up. You can do it one way or the other way. It doesn't matter. When you're doing division, you can turn it into a division first inside and then the square root, or you can do the square roots first and then do the division. Same thing with multiplication. So you've got some examples for the chapter 5 in this section. It's not a very long section. I don't do all of chapter 5. We just go through and grab some things out of here to make some of this things you've already seen in other classes make sense.